My name is Holden Marceaux, and I'm the reporter presenting the results for the internal combustion engine experiment. First, a little background into how an internal combustion engine works. We have a 4-stroke, 13-horse motor in our experiment, a single cylinder. The first stroke is the intake. The intake valve opens. The cylinder moves from top dead center to bottom dead center, drawing the fuel-air mixture into the cylinder. The next stroke is the compression. Both valves close and the piston moves from bottom dead center back up to top dead center. Once it reaches top dead center, the spark plug fires and ignites the gas in the engine, beginning the reaction. The third stroke is the power stroke, where the expanding gas pushes the piston back from top dead center down to bottom dead center, turning the crankshaft. And the fourth stroke is the exhaust stroke, where the exhaust valve opens and the piston moves from bottom dead center back to top dead center, forcing all the burnt gases out. We did 2 different tests for this experiment. The first was constant load, varying speed. For this one, the engine begins at idle and revs up to full throttle. As the engine's moving to full throttle, the dyno is applying the load. We did 4 different tests at 4 different loading, 0%, 10%, 20%, and 30% of the total possible load. These are our results. This is 0% of the load, 10%, 20%, and 30%. As you can see, at 0%, our torque and horsepower are pretty low. The power is on the bottom here, the torque's on the top. As we move to higher load, you can see that the torque increases much more quickly than the horsepower. So the motor needs a lot more torque, a lot more quickly to run at the same RPMs at the different loads. The next testing that we did was at a constant speed and varying load. So we started the engine running at a constant 2,500 RPMs and started at 0% of load, increasing every 5 seconds until we reached 40% of the maximum load. We repeated this process 4 times. Here we have our results from that. You can see they're all about the same. And as with the previous experiment, specifically to this one, you can see where our increases are every 5 seconds as the loading goes up. And as with the previous test, you can tell that the torque increases much more quickly than the horsepower does. It would be possible that the horsepower could outpace the torque at some point, but it would have to run to a higher RPM, and we never reached that RPM in either one of our experiments, or either one of the tests that we did. So our horsepower never surpasses our torque in any of our testing. Next, we have a few calculations. The first is our air mass flow rate, which is the rate of air flowing through our engine. These are all done for our second testing, our constant speed variable load tests. You can see our numbers here, they're all about the same. We have a relatively low mass flow rate of air through this engine. I mean, it's a small motor, it's a single cylinder, so it's like 420 cc's, I think. So you wouldn't really have a ton of air moving through this thing because there's not really that much combustion going on compared to like a car motor. The next is our volumetric efficiency, which is the effectiveness of the engine at getting air into the cylinder to combust. And as you can see, it's pretty high for this motor. This number usually ranges between 80 and 90%. We're above 90% in all of these, but I mean, this is a very small engine, so the air really doesn't have to travel very far to get into the cylinder to be combusted. It just has to basically go through an air filter and a carburetor, and that's it. So it's pretty efficient getting air in there. The next is our conversion efficiency, which is basically how good the engine is at converting the energy from fuel into the energy that's actually usefully produced. Not very good, but we're also running at less than half of the engine's possible, total possible load, and so we're running at very low RPMs. And generally, engines have a sweet spot where they're the most efficient. And as you can see, this is not what that is. Okay. Next, our mechanical efficiency, ratio of the useful power delivered by the engine to the total power it's rated for. So this is a 13 horsepower engine. As you can see, we're not really using that much of that power. This again is because our RPMs are low and we're not really operating at this engine's maximum potential. The last part is our brake mean effective pressure. This is the ability of the engine to obtain and provide high airflow and use it effectively. It's just the pressure which it effectively uses the airflow. This is just one of the things they want us to calculate in the lab manual, really. And that's it. Any questions?